University Zeyu WANG. He's an assistant professor in the Trust of Computational Media and Arts and Artificial Intelligence at the Hong Kong University of Science and Technology. He also holds a joint and affiliate appointments in the Division of Emerging Disciplinary Areas and the Department of Computer Science and Engineering at the same university, and he leads the Creative Intelligence and Synergy Bank. CIS or CIS in short. We are very happy to have you here. Thank you for accepting our invitation.
Thank you so much. Good morning, everyone. It is my great pleasure here to visit Koç University, and also my first time in Istanbul, in Turkey. So super happy to be here. So actually, Matt and I met at Yale when I was a PhD student. I remember like maybe 6 years or even 7, 8 years ago. So it's been a long time. I'm super excited to visit here and this lab. So today I'm gonna share a few recent works on what we call synergistic human AI content creation. So we know generative AI has been evolving very rapidly in terms of text to image, text to video, and whatever 3D content you can generate, right? So so today I'm going to show you some of our recent research in this direction. So just a bit of background. I think we all know, there is a strong connection between the content we create and the tools we have available to use. So here I show some examples of both Chinese and Western art. So you can see that we have the brush and mineral materials so that we can create very artistic painting like this. And on the other hand, we have the hammer and chisel. So this is essential for Renaissance, for the sculpting art. So moving on to today, we know that digital technology has revolutionized content creation. So this is some of the early examples. Do you know what the left top picture is, like top left? Do any of you have any idea what this image is about? Yeah, this is one of the early MIT graduates named Evan Sutherland. I think he was doing the sketch pad. So remember that was back in 1960s. Okay, 1960s, and the computers were huge and the screens were super small like that, right? But back then you can see that using that early hardware, they created interface that use sketching as a medium, so you can manipulate vector and also draw a vector like that. So that was very, very early digital tool that we can see. And now moving on, we have the all sorts of digital films and also interactive games that we can make. And all of these are powered by digital tools. But on the other hand, if you have ever created anything, for example, in Blender or using Maya, you know how difficult it is to build good digital assets. For example, traditionally, if you want to build make a model of the building like this, you will need to do first very detailed geometric modeling. This is based on mesh, and typically, this is an example I found. It took the modeler about 12 hours just to build the geometry. Okay, and once you have the geometry, you also need to assign textures, right? So like the bricks texture, the texture for the window, things like that. And also it'll take a large amount of time before you have a first version that can be used in actual production. And this is another example that I like very much. So this is a screenshot of a game, I think. And you can see the cost of the digital assets there. Okay, so the hero character costs about $50,000 just to make. You can think about how to model that person, how to model the motion, and things like that. And to make a very realistic scene, you need to do a lot of amount of work to make that happen. One thing that I like in particular is the trash on the bottom right corner. You see how expensive the trash is? Okay, it's like $3,000 for the digital trash. I may as well just make some physical trash and scan it, right? So you can see how ridiculously expensive it can be for assets or digital content creation. So we know that the reason why this was so expensive is that the digital workflow can have a very steep learning curve, right? So if you on the right you have the Maya, and then you can see there are a lot of buttons in Maya, and frankly, I don't even know what those buttons do, and it's very difficult for a novice user to create a shape like this. But on the other hand, if you look at something on the left, you see the architect sketch. So this architecture was called Ingolf Rink at Yale University. And you can see originally when the architect designed such shape, they just used very sparse strokes, some sketches to convey that visual idea. So you don't have to actually build very detailed 3D model to convey that visual information. Okay? So you can see that what is a good interface or good medium? It should be spontaneous and flexible. It should be able to quickly convey the visual form and also be suitable for exploring ideas. So one of the reasons why sketching is important or fundamental is that you can just draw strokes very quickly and to experiment with different shapes or different designs. But on the other hand, if you look at current graphic software, there are of course many buttons and windows. Sometimes a 3D interaction can be unintuitive on a 2D desktop interface. Okay, and also it's very slow to iterate design ideas. So moving on to recent years, especially since 21, 22, there's a huge amount of work in generative AI. From this is especially text to image generation, and these are some of the earliest text to image models, and from today it looks like ancient historical models, but still it's very rapidly evolving. So a key question I would like to discuss with you guys here today is how can we understand and enhance the creative process to build creativity support tools in the age of generative AI? So I think this is something we're super interested in because generative AI is great, but how to leverage that to build interactive creativity support tools, and especially how to enhance the creative process for content creators. This is a key concept or key question I'd like to discuss. Okay, and to answer that question, it involves a lot of interdisciplinary research. There's computer graphics for 3D modeling, 3D generation. There's HCI. You need to understand how users can interact with the system that you built, and also of course AI, right? So the latest AI models and things like that. So today I'm going to cover some methods and systems for what I call 2D, 3D, and 4D content creation. So the outline here is quite simple. I just wanted to introduce some of our recent works. The first one, Magic Scroll, is about scroll painting generation, and Head Evolver is a method for modeling digital human avatars. And then we have a neural canvas work that is focused on 3D sketching and in combination with generative AI. And Anycraft is to use physical objects, like everyday objects, as a proxy for character animation. Okay, so this is like the domain of the work I'm going to discuss today. So I'm just gonna jump right in. And I think during the talk, because I think we have quite a few in the audience. If you have any questions, just raise your hand. Okay. I really enjoy being interactive rather than just myself speaking. So if you have any questions, feel free anytime. This is intended to be an interactive and this kind of communication. Okay. Yeah. So the first work is for scroll image generation and was just published in VR this year. As you can see, the scroll image is just something like this, or technically it can be called non-typical aspect ratio images. Okay, so to use like DALL-E or some earlier models, we can only generate one-to-one square images. It was not trivial to generate images like this in a coherent and controllable manner. So you can see that this was also inspired by Chinese culture and comics, things like that. As you can see at the bottom, this is this is called Along the River During the Qingming Festival. This is like one of the national treasures in China, where we have a super long scroll image that depicts the entire city, the entire capital city of China about 1,000 years ago. So we took inspiration from there and was thinking, is it possible to generate a scroll image from a text description? And you can see, the scroll image is not repetitive. It tells a story, from different places to places. So as you can see here, these are the three examples we would like to kind of achieve using our techniques. Okay. If you look into it more closely, you see that scroll image generation is not trivial because it involves different levels of hierarchy. Okay, so you have a hierarchy where you have the entire scene, and in the scene you have different objects, and the scenes should be connected smoothly and to tell a story or to convey a narrative. So this is also an inspiration that we needed a multi-level approach for such generation tasks. Here you can see like a research gap compared to existing methods. You can see that some of the examples, have insufficient content, repetitive objects. Some of the visuals were incoherent because of the flaws in generative models, and also sometimes it's less controllable in terms of style and layout. So in our work, we proposed a diffusion-based framework for generate scroll image paintings. And I think the key technical thing is here we have a series of story-inspired visual forms and also a VR system and user study. So if you look at the pipeline in the bottom, you can see that we have 3 layers, and specifically for like foreground, middle ground, and background. So this has an impact on the generative results. Yeah, so here in the workflow, I just wanted to briefly show that it has a couple of modules. Okay, so the input is just text. Okay, you give it a text description, and the final output is a scroll painting that's supposed to be coherent, controllable, and consistent in terms of style and layout. So it has a couple of modules in it. So the first is GPT-based layout prediction, where you give GPT the text description, and the GPT can tell you where the different objects are supposed to be in the painting. Okay, so if you say like, dwelling in the mountains, I make friends with trees, so they know that the mountains should be like, in the middle of the painting. And maybe there's there's sun, and the sun should be like at the top part of your painting. So these knowledge can be inferred by the current GPT models. And after that, we have this text-based style control in the middle, and also the semantic aware denoising that basically have the denoising process at 3 different levels. So and then finally blending latent together to generate this coherent scroll image print. Okay, so I won't dive into the details because I think there's still much other content, but I'll just briefly show you how this works. So you have the introduction, you have the descriptive text, you put them in GPT, and they can GPT can give you the layout as this. For example, scene 1, it can generate a bounding box. And the objects, they can generate a bounding box. And finally, we can have a layout like something at the bottom right corner. Okay. And for the multi-level denoising, you can see that it's pretty much the standard diffusion process, but we have the 3 layers so that we can blend the latent together and then finally do this latent smoothing to generate a more coherent result. Okay. So this is also kind of took inspiration from like painting theories where you for example first paint the background and then the middle ground and then the foreground objects. So this is also beneficial for this kind of generation task. All right, so let's see some examples. So here you can see that we have different types of results where if you don't have latent smoothing, you can see that there is a transition artifact, like a vertical column or vertical scene. If you don't have the object mask, you can see that there's supposed to be the sun, but the sun just disappeared because you don't have the object mask. If you don't have the scene mask, it also cannot be blended very well. So here shows the style control. You can see that the top is the full painting, and then if you don't have the style control, you can see it's not it's kind of more photorealistic rather than Chinese painting style. And if you don't have the image-based style control, you can see at the bottom example where they are still connected, but the color and the style there is not very coherent. So there's a lack of such control. And we can also warp these images into VR so that if you build a VR application, you have a more immersive experience, using our generative images. So this is some blending techniques. We also have a data set for painting, comic, and cinematic panoramas. In terms of evaluation, I'll just give the details. I just wanted to show you some of the results, like here. So you can see the bottom row is our results. You can see that they're coherent and more, controllable. Especially if you look at the bottom right corner. Okay, so this is like an army marches in the mountains and then fights the evil dragon, something like that. So if you see, if you look at it from the left to right, it tells a story. Okay, you see the army, you see the mountains, and then you see the fighting. In comparison, if you look at the top few rows, you don't see such narrative. Okay, and sometimes they are just repetitive, and they don't tell a story, and the kind of style control is just not as vivid as our method can provide. Okay, so you can see the repetitive patterns there. And so here's also some examples. Top right corner is ours, and the other ones are less kind of appealing in terms of, and you can see the repetitive patterns. Here is the comics. It's funny that if you use ControlNet or maybe one of the early versions, they can generate like a stack of comic books rather than the comic itself. So sometimes you can see the confusion like that. And here's example like I showed, the army marches to the mountains, and whereas the other ones is less coherent or less kind of narrative oriented. And what's interesting is that we can turn this into videos. Okay, so we generate a scroll image, and then we can use runway or other video generation methods to generate video like this. And it's quite amazing because you can see the depth, you can see the camera transition. Okay, let me try to play this again. The bottom right corner, right? You can see, just zoom out, and then you can see the kind of immersive environment that our painting can provide together with the video generation techniques. Okay, so here in the top right corner, you can also see the fall, right, and the springs. This is also kind of the amazing thing that the video generation will provide. So here are some other examples, like here. And the benefit of our method is that it can generate arbitrary aspect ratio images. Any height and width you can specify. Okay. So I think we have some other examples. So this is very extreme example. This is 40:1. Okay. This is 40:1 image generation. So you can see like I forgot the exact text, but you can see like the two girls in the forest. You can see the rivers and lakes, and pretty much most of the contents is still very coherent. And then moving on, you see like the mountains and the castles on the far right. Still, so the idea is that it's super coherent, and you can specify whatever aspect ratio you can generate. So this can be useful for art installations if you have a super long corridor. So this can have some practical use as well. Okay. All right. So briefly summarize this work. So basically, it's a diffusion-based framework for scroll image generation, and took inspiration from the paintings and some art theory, and then the key technical part is the multi-level diffusion, so that we can make it more coherent and controllable in terms of style and layout. And the code is available as well, so feel free to check it out if you're interested. Okay. All right, I'm just gonna pause here for a little bit and see if there are any questions. Yes.
I have two quick questions. Do you ever train your LLM for layout? Because there might be like very different aspect ratio that LLM haven't seen with training goal. Do you ever fine tune it?
No, we just use on the shelf large language models, and we can prompt it, but we never fine tuned it.
Okay, it's like interesting because like I wouldn't expect LLM to predict the position of the the objects in a like large aspect ratio. The second question is, do you pre-train your diffusion models or do you fine tune some already existing models like stable diffusion?
Right, for the diffusion part, we fine tune that because the existing diffusion model, they were trained on a large amount of data. And in our case, we have the data set for scroll paintings, and then we fine tune on the painting on the data sets. Yeah. The first question was great because we also realized this was a surprise for us as well, because you never know like what large language models can give you, right? And sometimes they can get very plausible results. Okay. Any other questions?
Normally these diffusion models, there's trouble handling very large textual descriptions, right? So how did you handle that, since in this case you probably need quite detailed descriptions to generate such a large aspect ratio?
Yeah, in that case, I think the key part is the multi-level process, so that you can given the text description, the GPT you can ask GPT to extract the key objects. For example, the girls, the castles, something, and then based on the layout, you can put them in the plausible positions. So I think this is the benefit of combining the GPT and also the multi-level diffusion process.
But when you like create a layout, it's like a segmentation, is something like that, right?
Yes.
Do you still give the textual input to the diffusion model, or do you just give the object layouts?
Give them both.
You give them both.
Yeah, just to get more information.
Maybe a quick
Yes.
question from my side. What is the typical length for the text each write? Like, and is it kind of stable across the length, or depending on the variation in terms of, let's say, some other synonyms or whatever?
Yeah.
Does it generate something similar, or how stable it is across, let's say, variability?
Yeah, this is a terrific question. So the original motivation for this is actually Chinese poems. So like for a lot of Chinese poems, they just depict like scenery in nature, things like that. So typically a Chinese poem consists of 4 to 8 sentences. And then we just throw them, or we can translate them into English, and then just feed them as input to our model. So typically it's like 4 to 8 sentences. And this is something, a lot of results are generated based on that length of input. But we can also give it longer descriptions, like the 40:1 example. That's just very, very long. We didn't do a specific evaluation of how long it can be, but most of the examples is from like 4 to 8 sentences.
Gotcha. And another question about, let's say, the temperature parameter, let's say, in that have you ever explored anything toward that tension temperature or sampling temperature? Does it just have any effect on the results?
Oh, so I think for the temperature parameters, we didn't specifically do any ablation studies or tests on that. We just focus on the multi-level thing so that we can have some.
So you go with the default choice?
Yes, I think so. Yeah. All right. Thank you for the question. Okay, so let's just move on, since there are other 3 works remaining. Okay, so this one is about text avatar generation. So previously it's about text to image, right? It was very long scroll image. And this one is about a 3D head avatar model. Okay, because this is very useful in a lot of applications like games and animations. So here we just wanted to use the power of generative AI to generate a mesh-based avatar model. Okay, so you can see the overall pipeline like this. So again, the input just text, and then we can generate a very high fidelity head avatar model in mesh together with very high quality texture. The benefit of that is that we can preserve all the attributes for editing, like the 3D parameters or the blend shape and the rig, so that you only need to animate it once. After that, you can use our model to transfer it to another person or another character, and all the animation parameters will still be preserved. So In text to avatar tasks, there are several challenges. So the first one is matching. Is always, matching is not super good because a lot of maps are based on nerf and they don't care of that. They just care appearance more than the geometric structure or matching. And also some implicit representations, they cannot preserve shape attributes because again, you convert it to nerf and then you extract the mesh and then all the blend shapes, rigs, they're just gone. The third challenge is sometimes there's over smoothing in deformations. So this is some of the Euro-Jacobian fields work, or they use the AI to drive mesh deformation, but sometimes the deformation is not expressive enough. Okay, so we wanted to make it a goblin, but the ears are not long enough. And finally, some generation is dependent on parametric models. Maybe you must have a flame model or have a simple model for it to work. If you don't have it, then it can be challenging. So here, our pipeline is we have two inputs. The first one is the text on the top right corner. That's the one input. The other is we give it a template mesh. So this is something to note. We give it a template mesh. It can be a parametric model, or it can be any model with good quality meshing. That'll work. That's a good starting point for deformation. And then we use something we call a vector field. This is like a modified version of Euro-Jacobian fields so that it can drive the deformation to fit the expected shape that was described in the text. So here is the terracotta army. So you can see after deformation, you have the deformed mesh like that. Okay. So with that mesh, we can also project it and use SDS, score distillation sampling, to generate the texture for it. So you can see through the optimization, we also generate the albedo map and things like that. So finally, we have a shaded version or have a full 3D model for the avatar. So the input is we have two inputs and we optimize the vector field, which is deformation, and also the albedo map, which is like the texture. And our key contribution is the Jacobian field right here. I don't know how many of you are geometers, like super into geometry. But I won't talk, speak too much about this, but was one work of Euro-Jacobian field published on ZBrush in 22. And our version is that we give it more degrees of freedom. So in Jacobian field, there is only one direction that you can optimize. But here we make it three directions. Basically, we increased the degrees of freedom from 1 to 3 so that it can be more expressive to capture the shape of the terracotta army, for example, like here. And you can see the effects of the vector field in comparison with the Jacobian field. So with the Jacobian field only on the left column, you see that it's not super expressive. You can still see, they are more, homogeneous in a way. And typically, if you don't have a good enough results, you increase the learning rate, right? You want to make it harder when you optimize. But if you increase the high learning rate, on the second column, you see that they're distorted. They are no longer symmetric or things like that. So it doesn't work if you just increase the high learning rate because it's just not expressive enough. Okay, so use our work. We have a 1 degree freedom version and 3 DOF version. You can see that on the far right, using our version, it's just more expressive in terms of the ears or the eyebrows or the horn of the rhino. So this is the benefits of our method. Okay, so here we also show the amount of deformation here. So you can see the terracotta army, the top part of the hair, this a block of hair, this is deformed a lot. For the monkey, it's a part below the nose, and for the pig, you can see the nose and the ears are the parts where it's deformed a lot. Remember, the starting point is only a template mesh. So the template mesh is just a regular person, but with a person you can deform the ear to make it a pig, something like this. So this shows the expressiveness of our method. And again, compared with NGF, the Jacobian field, our model or the deformation can converge faster because it's more expressive. You can see it requires fewer epochs for it to converge. So here you can see some of the comparisons. So ours, we have a better matching. If you zoom in, you can see matching is good compared to Tada and Fantasia 3D. And here is also more examples. The thing is, because we start from a template mesh, and the template mesh typically has good matching. So our deformation can ensure that the deformed version also has good matching. Compared to other methods based on nerve or other implicits, it's never guaranteed. So here is a textured version. You can see we have the the Superman and the Trump and Van Gogh. You can see that the generated version, I think they're good enough. And the other thing is that it's mesh based. We can do all sorts of things with geometry or with graphic software. Animate it, rig it. A lot of things we can do. So here you can make it speak, right? So you only rig it once, and after deformation, the rig still applies to the model. You can, you can convert, you can modify the shape and the expression parameters. You can do part-based editing. Only edit the nose part, for example. You can also edit texture based on text. So these are some of the application scenarios of our method. And what's nice about it is it can be actually used in graphic software. So you can just do some modeling and put them together. You can do the morphing process. And these are the diverse categories of characters that we can generate by different textures like that. All right. So just to briefly sum up, this is a work where we introduce a per triangle vector field to enhance the expressiveness of mesh deformation while preserving 3D attributes. And our generative avatars can be seamlessly integrated in graphic software because it's mesh-based, and a lot of the animation parameters can be preserved. And the last part is that our method can be integrated as a plug-and-play solution for enhancing deformation processing. So if you're interested in how AI or how like text-based input can drive or can supervise or can be used for this kind of mesh deformation, this is something you can look at in detail in the future. Okay, so we also have some more details available via that link, so feel free to check it out if you're interested. All right. So I'm gonna pause again and see if you have any questions related to this work.
Is it like quick? I feel like even it works like pretty well. So like it might take quite time, which might not be feasible for many people.
40 minutes
40 minutes
on a single GPU, yes.
Yeah. Single result, right?
Yes. So it's not fast. Yeah. Yes.
And Zeyu, I have a question as well, like a general question about cost. Can you give us an estimate of how much it costs in dollar terms to generate these videos per minute or per hour?
Okay, interesting. So let's see. I'm not sure if I can give you an estimate in US dollars, but for this, because this work is not based on training, this is based on optimization. So if you have a text description, I can use a single 4090 GPU to optimize it for about 30 to 40 minutes. So you have something like we show on the bottom right. So this is like the estimate I can give you. I mean, you can compute the cost of purchasing the GPU and the cost of electricity, I guess, if this is what you're asking.
All right, thanks.
Okay, thank you.
And so what kind of neural network architecture that you're using? So
The graphic software?
no, neural network architecture.
Neural architecture. So, okay, so this is based on Jacobian field. So let's see, here's more example. So basically it's, okay, so first it, for the Jacobian field, it has a bunch of parameters for you to optimize. Okay, so you have the deformation parameters, and it's based on optimization, not training. And here you can see the pipeline. So we do have a stable diffusion to compute the SDS loss so that we can generate texture. And we also use a landmark control net to feed into the stable diffusion when you compute that, and we also compute the landmark and opacity loss during the process. So I think these are network structures that are involved. And on the far left is the Jacobian field, it's the neural Jacobian field and the vector field that we're optimizing. So once everything's connected, it's differentiable, and you can just optimize along the way. All right. Okay, thank you for the questions. And moving on, I'd like to introduce also something about 3D generation. Okay, but this time is related to sketching, and also in combination with generative AI. So we know that sketches are again very useful or very flexible in terms of design. So here I give you a specific task, which is scenic design. So this is something if you go to a musical, you see some the props right on the stage, and actually designing such props is not an easy task. There's a lot of iterations and also building the physical models, things like that. So this is a task that we want to build a tool, build a system for. And traditionally, there are a lot of different tools. So the first one is mood board. So mood board is something where you just collect a bunch of pictures reflecting the appearance of the mood. Okay, so maybe this is a very sad scene, and you just want to collect a lot of dark images, so that provides you a mood for the specific atmosphere. But the thing is, the mood board doesn't have anything to do with a specific 3D scene, right? It's only represent the appearance or the overall atmosphere, not anything related to 3D structures. And sketching is great. A lot of designers use sketching. But again, even though it conveys a 3D idea, the sketch itself is drawn on a 2D piece of paper. So it's very hard to convert it to an actual scene or actual scenic design on stage. And of course, we can always mention that the use of 3D software is terrific, it's terrific, it's very powerful. But the thing is, okay, so you have to be very fluent in such software. You have to do all the geometric modeling in detail and also the appearance modeling, like I mentioned at the very beginning of the talk. And finally, the other solution is to use scale model. And this is actually used a lot in art schools and design schools where they just build the physical models and then move it around and see if the design makes sense. So this is a very traditional way. But again, the cost is very high, and if you make something wrong, it's very hard to modify that physically in comparison with the digital version. Okay. So we did a kind of a formative study to get some insights from the professional designers, like the stage designer and media artists, and we basically summarized this design consideration. So for such a tool, it should be supporting efficient creation of appearance, and also supporting intuitive actualization of spatial concepts, and also support rapid idea exploration and design iteration. So basically, you can see that the mood board appearance check, but spatial concepts and iteration not so much, right? And for scale model, it's also very hard to iterate. So we wanted to propose a system to support all 3 design considerations, and this system is something we call a neural canvas. For those of you who are interested in system development, this is architecture. Actually, I started writing the code for this project back in 2019, so it's been quite a few years before this was published. So a lot of engineering effort, but the thing is we have, this is a web-based interface, as you can see here. A web-based interface, you can go to a URL and you can just use it. And the interaction all happens in the front end. And then we do have a backend for AI-related functions. For example, you give it a text or give it an image, they can run the deep learning models on the backend and then feed the results back to the front end. So this is like the interface we built like this. So you can see a demo like this. Okay, so we have a 3D sketching. and we can convert it to a scene like this using generative AI. And this is very fast. This was done in like 10 minutes or 20 minutes. You just draw the 3D strokes in the interface, and then you can use generative AI to assign texture to it. So this can give you more like a immersive experience very quickly. If you do this in traditional software, I think it can take longer to build such a thing. And of course, it can be used on desktop, on tablets, things like that. And one key insight is that we want 3D sketches as a very nice control for generative AI models. Okay, so here we can use feed in the current canvas, where you can screenshot the entire screen and generate images based on the sketch condition. And on the right, we can also do partial generation, right? So we have the background image, for example, like this, and then you just draw some sketches and as the front, as the foreground, and then we can generate a very coherent scene based on this condition. So it's very intuitive way to provide input or provide condition to generative AI models. So for those of you who don't know what a 3D sketch is, it's a super simple. You can project these 2D sketches onto different planes, and then you have a 3D sketch. So basically, just strokes placed on canvases in the 3D plane in the 3D space. So here we can also project the images generated. So you can see here is the sketch and the generated image, and then you can project them back so that they are on different layers of the scene. Okay, so it's just like an illustration. And we integrated a lot of AI functions because traditionally, if an artist wants to use some AI functions, they can go to like Stable Diffusion or some other platforms. But the thing is, for such platforms, everything you can only use one model at a time, and it's not good for iteration for prototyping. So in our system, we integrated a collection of AI tools, and we found a significant improvement in terms of the interactions of different AI models. So here we have text to image, sketch to image, in painting, out painting, a lot of different functionalities, and also segmentation and other 8 functions. So here you can see that we have a user study, and on the bottom right, you can see the bottom right are the 2 scenes that we created. So you can see that the left one is the aquarium, and the right one is looking out of the window. You can just zoom out and have an immersive tour. So these are the 3 scenes that we can support generating and creating, and this is based on the integration of 3D sketching and a collection of generative AI models. So I'll skip the user study part. I'll just show you some insight. I think this is important. So first is that integrating multiple generative AI models can facilitate prototyping. So from the user perspective, if you have to go to different platforms for just one single model, you can never explore the interaction between the different models. So integrating multiple generative AI models actually make a significance in that regard. The second one is 3D sketching can facilitate AI content generation. I'll give you some specific examples for that as well. Okay, so like this. First, 3D sketching offers control over viewpoint for generative AI. So if you think about generative AI, there are a lot of sketch to image work, right? Where you just draw a 2D sketch and then generate an image. But if you think about it, all the AI models are trained on photorealistic images, on real images, which has a correct perspective, right? Or have the correct camera model. But when you sketch, you can never guarantee that your perspective are correct, right? If your perspective is off, then it's not one of the training data that the AI models have seen, making the final generated results limited, okay? Because the perspective may be wrong. And here, 3D sketching can, can change, can control. So you can see we have a 3D sketch like this. Viewing from this point, we can generate a scene like that. And then you can slightly adjust it, and you can generate another viewpoint, right? And then you can also change to another viewpoint, and then you can generate different types of AI images that you want to use. Another thing is about the perspective. So here, originally you have a 2D sketch, and after projection you can have a 3D sketch. We can see the windows are wrong, right? The perspectives are wrong. So you can fix that in the 3D sketch. And then after you fix the perspective and the proportion, things like that, it can serve as a better control for generative AI. But I think this is super important insight that we found out in this work. Okay. All right. So to quickly sum up, we propose Neural Canvas, which is a tool to facilitate scenic design prototyping. We integrated the multiple generative AI models and also 3D sketching, so that we can provide a better intuitive control interface for AI generation and for scenic design prototyping. And the key insight is that 3D sketching is useful. It can facilitate AI content generation compared to 2D sketches where you may not guarantee that the proportion and perspectives are right. So this is a great way to control that, and also for the viewpoint, things like that. Okay. Yeah. So this work was also published at KAI last year, and we do have the web interface available, but we don't release it to public because if everyone uses it, the backend will not be able to handle all the requests. But the front end, we do have everything available. So if you're interested in using this, or if this is any, could be any help for your research, feel free to reach out to me afterwards. Okay. All right, so I'll move on to the last work, and we can have some discussion, all together. So we talked about 3D generation, right? 3D, avatar generation and scene generation. So this work focuses on animation, character animation, and especially in mixed reality. So why is this important? You can see that in animation production, we always have a prototype, right, on the left. So on the right is the final production. On the left is the animation prototype, where you have the rig and the motion, things like that. So this prototyping process is very important before you make the final production. But again, this can be exhausting, right? You remember the theme of the talk today. If you go to Maya or go to the animation software, it's super heavy, and you can see the timeline, right? You need to adjust each joint and how it changes over time, and this is a very tedious process. But if you've ever been to like IKEA, they have this figure model, right? They have the figure model where you can just physically manipulate the gesture. And I think physical manipulation is much more intuitive than an interface like this, right? So we just wonder, like, is it possible to use physical animation, physical interaction, rather than this digital way, right? Because we're making a 3D animation and using a 2D interface is just limiting. All right. So we propose AnyCraft. This is a system where we use physical proxies, everyday objects like this, for character animation. Okay. So the idea is to use the everyday objects you can find, and then you can manipulate it in the physical space in MR, and then you have the animation prototype generated from that. So these are some of the examples. So here we basically there have been some previous work related to this, basically physical rig and physical manipulation, and our work focuses on generating animation prototype based on everyday objects. So the overall pipeline is like this. We have several cameras to track the markers, and the user will wear a Oculus head-mounted display to manipulate that typical objects, and then you can, based on different material, different objects, we can generate animations like this. Okay. So you first select a character in AR, and then you fabricate the physical proxy. This is actually very creative. So you can use like wires. You can use like cables like this, right? You can use power adapters like this. Every object you can use, and once you put a marker on it, it can be a control point for the character. And what's nice about this is that you don't need physical simulation anymore. You are in the physical space. So you can, based on the marker, you can capture all the physical properties of the character. So I'll give you an example. So this is in MR. The user is making the proxy. See, is the wire, and then you just bend it very quickly to make a shape like this. Okay, and once you have that, you can attach the markers. Just a few markers on the legs, like this, and then you have the proxy for the character. Okay, and then you can select the virtual model, and then the rig is there already, so you can basically map the rig, right? You can adjust posture of the tiger, and then you can keyframe it, and finally, you have a complete animation for the tiger. So these are the key frames, and then you can see the tiger jumping. Okay, this is like how you make the character animation very quickly. Everything is in real time. All right. So we support a wide variety of materials. So you can see we have the 3D printing pen, the metal wires, cubes, origami, even magnets. Magnets can also work, and also clay, things like that. And so here you can see the eagle and the butterfly. This is all supported by the 3D printed material. This is about the physics that I just mentioned. Okay, you don't need simulation because everything is physical. So here you can just hand different objects, or you can use a helicopter to carry some box. So this can be all captured using our system. And you can also pose it differently. So here is you can use different cubes to pose different characters. You can make the chicken climbing on some columns, things like that. And you can also use the cube as a target so that the character can follow. So you can also make this interactive in this way. And this control is much more intuitive compared to 3D software. Okay, so again, user study. You can see in comparison with 2D animation UI, our system has significant strength compared to the traditional methods. And for evaluation, we just experimented with all different materials. And you can see these are the physical proxies that our users made. They are never trained for this, but it's very easy for them to make a proxy like this, like that. Very creative. And all different materials. We also have a study about each individual material, but I'll skip that for now. So I'll just briefly show you some other application and insights in this work. The first thing is that for rapid previs, we can use the marker as a camera, as a virtual camera. So you can see the left part is the preview of the animation. Okay, so if you're a director, you can use the cube to experiment with your camera moving in AR. And another thing is we can support multiple character interaction. So here is like an eagle catching a cat, okay? And the material are magnets. So when they are close to each other, they just attach. So by this way, you can intuitively show the eagle catching the cat. And finally, we have the environment proxy. So again, this is related to the neural canvas where you have the scene set up, right? You can use like the milk box for like a virtual objects, and then you can prototype this physical interaction very intuitively compared to 3D software. You have to model everything out. All right. So to sum up, there are some key takeaways. So we wanted to leverage 3D interaction so that we can support novice-friendly animation prototyping, and we enable that with support for different levels of detail and different types of material, so that they can, in the future, when we talk about an interface, maybe it's no longer a digital interface per se. Maybe it's a hybrid, right? Maybe it's we have the physical and embodied interaction in addition to the GUI interaction that we have now. All right. So these are some key takeaways. So to briefly sum up the entire talk, so my lab currently focuses on synergistic human AI content creation, and of course this I think is a little bit cliche if we talk about that now, but again I think AI should assist and collaborate rather than replace, and sometimes it's very hard to replace, and sometimes even if you replace artists, it may not be a good thing. You may lose a lot of inspirations. So this shows why interdisciplinary research is very important. I'll just show you this example. This is something I like this is something I experimented myself. So you can see if you have a sketch on the left, okay, this is an original sketch by Picasso. And if I ask any of you to draw the sketch, to replicate the sketch, if you're never trained as an artist, you may draw something like on the right, right? Like I drew for the first time something like something on the right. However, if you turn that upside down, and then you draw, think about what you can get. Okay, this is a very nice example from Betty Edwards, a very famous artist and arts education professional in the US. And this is my work. This is something I drew. Okay, I was never trained as an artist at that time, and I just put it upside down and draw something like this. And when I turned it upside right, when I turned it, on the right side, I was surprised. Like I never knew that I was such a good artist. Right? But why? Think about it. Like why could this be the case? The book was called Drawing on the Right Side of the Brain, meaning that when you draw something upside down, you don't know what you're drawing. So you tend to focus more on the detail and proportion and perspective of the thing that you're observing, right? Whereas if you just draw that in the original setup, then you know that this is the person. So you don't pay attention to the details of the geometry structures. You just draw what's in your mind. Okay, a person sitting on a chair. The person has two eyes and a nose, sometimes like something like that. So you will have something like this, right? Very rough and not artistic. But whereas if you focus on the proportion, you'll have something like that. So I'm trying to say that this calls for synergistic creative intelligence. Right? There are a lot of very good principles or good practice in art in content creation that current AI has not modeled yet. I think modeling such creative processes is very important. Of course, when the camera was invented, Talario said from today painting is dead, but painting is never dead, right? Painting evolves into different genres, and this is why we see the new artworks like those on the right. All right, so in the future, I think there are still many challenges that remain. I think computing and AI in general should support creativity by informing creative intention. Understand what user is thinking about and how to assist them, and reducing tedious repetition, and also helping explore broader design spaces. Okay, so this again calls for interdisciplinary research.